Okay, class. Here is the video that I promised you all. This is just a few slides looking at light, and as I mentioned uh, before in class, um, yeah, didn't quite have time to get to this, but I just wanted to go over just a few things. So we should be looking at part 2 of the light lab. You can use the information that I talk about because we can't really have a discussion in this format, but hopefully, we'll learn a couple of things as we go over this. So number one, what type of a wave is light? So if you think back to class when we were originally looking at the pre-lab questions, one of the things that I was asking groups as I was walking around is, what's waving? For example, when you think about sound, um, for anything for anything to produce sound, some source has to vibrate, whether that's a string or a column of air in a flute or your vocal cords, right? There's some source that's vibrating, and then for sound, wave propagates as pressure, as compressions and rarefactions through the air as it moves from point A to point B. So we need to think about light the same way and kind of ask ourselves the question, well, number one, what's vibrating in the first place? What's that source? And then number two is, then how does it propagate? Okay, so a couple of things on this slide to note. Light is a little bit odd. If anything, we call it a transverse wave. And even I hesitate to do that, but compared to, transverse or longitudinal, it's definitely in the transverse family. And then my question, so if light is a wave, then what's waving? And the answer to that is that really all light is, it's electromagnetic radiation, okay? And one way to understand this is to kind of think about the way that an antenna works. So for example, you have the antenna of your car, and it can receive and transmit radio signals, which is a form of light. Although the antennas in our car don't really broadcast. They could, but they're designed to just receive. Anyways, a radio tower that wants to broadcast light. So now we're looking at trying to answer that question. Well, what's waving? Well, any metal has electrons in it, and electrons are the things that are waving. And so what happens in an antenna is the electrons are accelerated up the antenna and then back down. And as they're accelerated and moved up and down and up and down, they create this changing electric field, right? So you have a fluctuating electric field, and then anytime you have a fluctuating electric field, which is kind of what a current is, we know that that produces a magnetic field, okay? So we have those two things where if we're looking at, okay, what's waving? Well, whatever the source is, it's moving electrons, okay? Moving electrons produce light. And in fact, if you think back to our model of the atom, right, we have the nucleus, and then the electron can be in all kinds of different things, right? And as it moves and shifts, it emits light, okay? As it drops in energy levels. Well, it's kind of the same thing on a very, very general level, right? This is one way that light is produced, but the other way that we can produce different types of light is by accelerating electrons in antennae. But the point of all of this is to say that the thing that's vibrating is typically an electron, and it moves through space as electromagnetic, now it's hard to read now because I've drawn over it like 1,000 times, electromagnetic radiation, okay? This electromagnetic wave where you have an electric field in one direction, and as that electric field changes in strength, it produces a magnetic field perpendicular to it as it moves through space. So, okay, sound you have a string or something that's vibrating, and sound propagates through space as a pressure wave. Light, you have an electron that's accelerating or vibrating in some way, and light propagates through space as an electromagnetic wave. It doesn't require a medium. Okay? So all waves require a medium. They need something to travel through, except for light. Light propagates itself, and that's a good thing, because if you think about space, right? If light needed a medium to travel through, then light couldn't get from the sun to the earth, because there's a vacuum between us. There's nothing there, right? So light has to be able to propagate itself, and it does in the form of electromagnetic radiation, right? This electric field and this magnetic field that, as they change, propagate themselves as they move through space. So that's what's waving. You have this fluctuating magnetic and electric fields. So how fast is light then? It's, what is that number? 299,792,458 meters per second. Or we round that to a nice 3 times 10 to the 8th meters per second. Okay, that's the universe's speed limit. Nothing can travel faster than light. And there's all kinds of you need to study relativity to kind of know why that is the universe's speed limit. Anything that has matter, it would take an infinite amount of energy to accelerate it up to this speed. And again, we're outside of the conventional laws of Newtonian mechanics, because if you look at Newton's second law, F equals ma, you should be able to accelerate any object up to any speed. Not, why stop at this? Well, that's where Newton's physics breaks down, and you have to rely on relativity to comprehend things that are moving that fast. So light represents the universe's speed limit. You can't go faster than the speed of light. We've done several different experiments to try and lock that down. This is one, at least a very simplistic model of a modern way of doing this. You would definitely not use a candle. You would use a laser. But you have this mirror here that's spinning really, really fast, and your laser light comes, it hits the mirror, it reflects down. D is normally like very long, like a football field's length, hits another mirror, bounces back, and then by the time the light gets back to the mirror, since you have it spinning so fast, it will have shifted a teeny bit. So instead of reflecting right back at the laser, it reflects off at some angle, and based on the amount of difference here in this angle, you can tell how fast the light had to have been traveling. And the greater the distance D is, and the faster you can rotate your mirror, the greater accuracy you'll have in actually like being able to perform that calculation. But before we had really cool things like this, I can't remember who, but some ancient astronomer used the fact that one of Jupiter's moons, Io, it would eclipse at slightly different times based on Jupiter's relative position to Earth. So you see Earth is closer to Jupiter here, and it's further from Jupiter here. So Io would eclipse. It would take a little bit longer to eclipse in this scenario than predicted, and that's because the light had to travel this extra distance. And so they were able to get a close approximation of the speed of light, but still off from like the number that we use. And actually, I believe that Galileo, I can't remember who it was, somebody tried to use lanterns. They would like a person with a lantern on the top of one hill and a person with a lantern on top of another hill, and the first person would unhood his lantern, and then the second person, as soon as he saw that, they would unhood their lantern, and they were trying to use the time difference, the time delay between the unhoodings of the lantern to calculate the speed of light. But over those distances, human reaction speeds are slower than the light travels. So yeah, you can't do it that way. Anyways, so that's the speed of light and a few stories on how we've measured it. This little link, I'll put the link in the announcement. So those of you that want to watch it, it's a TED Talk. It's pretty cool. Anyways, so the electromagnetic spectrum. We talked about this as well a little bit in class, and what we're trying to show here is look, we see this much of what light really is. I mean, and even this little bar here is a gross misrepresentation of the span of like all the different types of light that there is. Anyways, all we see is the visible part of the spectrum, but there's so much more to light than just that, right? You have radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays. They're all light. They're the exact same thing. They're just fluctuating electric and magnetic fields. They just have, as you can see, different wavelengths. Radio waves have the largest wavelengths. Gamma rays have the shortest wavelengths. Different wavelengths and different frequencies. One of the things to note is we know we have this little equation here that lets us calculate the speed of a wave. You would have used this in the Slinky part of the lab. And with light, all types of light travel at the exact same speed. It doesn't matter if you're visible. It doesn't matter if you're a gamma ray. All light travels at the exact same speed. And so that's a constant, which means that these two variables here have an inverse relationship. If the wavelength is going to go up, the frequency will decrease proportionally, right? So if you double the wavelength, the frequency is cut in half because the speed has to stay constant. So we have all these different types of light. What are they used for? I like this chart, and so you can spend some time if you want to looking over this, but it gives, you know, some characteristics of like the size. So for example, you can see here's the visible sliver right here, and visible light is about the size of bacteria, right? And then as we get smaller, ultraviolet wavelengths are the size of viruses. X-rays are down here the size of individual molecules, atoms, and then gamma rays, you're looking at the size of subatomic particles, okay? But if we had the other direction getting larger, infrared light is about the size of cells. Microwaves are about the size of baseballs. And then the radio spectrum is, right, from people-sized to football field to mountain-sized waves. So just to kind of get a feel for like the size of those wavelengths. And then underneath here, you can see some of the applications. And so this is one of the things that the lab asks about is, we have all these different types of light, but what are they good for? Can we use them in any way? And we absolutely can. Visible light, that's obvious, right? We see with it. Ultraviolet light, that little light that the dentist sticks in your mouth to harden the fillings, that's UV. Tanning beds, suntans, right? That's all that stuff. X-rays, I think that one's pretty clear application, right? And then gamma rays, astronomers use it to observe faraway astronomical events. And then the other thing we use gamma rays for is in cancer treatment. Typically for cancer treatment, folks talk about either radiation or chemotherapy. And chemotherapy is just chemical therapy. You just take a lot of drugs to try and battle the cancer. But radiation, they're actually using gamma rays to shrink the size of the tumors by killing the cells. And then the other direction, in the infrared space, our remotes operate in the infrared spectrum. I don't know how many of you have ever played the Wii, but with the Wii you put that little bar up on top of your TV, and that's an infrared light emitter. And then the remotes sense the infrared light coming out of that bar. And so one of the things you can do is, if you have a remote like that, is you can point it at anything that's warm. Like if your oven's on, you could point your Wii remote at the oven and it would work, just like as if you were pointing it at the screen. Anyways, moving on, microwaves. Our cell phones operate in the microwave system. Microwave ovens operate little bit different wavelengths than your cell phone. But most of our small communication devices use microwaves as a way to send signals. And then radios, obviously, the AM, FM radio stations, television broadcasts, radio towers. I'm not sure why ultrasound's on here, because I'm pretty sure that uses sound and not light, but maybe I'm wrong. Anyways, so those are some of the uses of the different types of light that we have. Last slide is considering the energy nature of light. And again, this is another space where light breaks some wave rules. The first rule that it's already broken is that light doesn't need a medium, right? It can propagate without a medium to pass through. And so the other rule that it breaks is every other wave, the energy that a wave carries is normally proportional to the amplitude. Normally it's the amplitude squared. So this is for normal waves, sound, waves in a rope, water waves, whatever. This is normal. You can tell how much energy is in a wave based on its amplitude. With light, that's not the case. With light, increased amplitude, meaning that the light is bright, all that means is that, let me change this. There are more photons, okay? The more electrons things comes from the photoelectric effect, but we're not going to dig that deep into what the photoelectric effect is. But really bright light just means that there are a lot of photons coming in. If you want to know about how much energy is being carried in the light, that has to do with frequency. Okay? The higher the frequency, the higher the energy carried by the photons. So if you look, right, gamma rays have the shortest wavelength. So, right, their wavelength is small, so that means their frequency must be huge. Radio waves, on the other hand, have huge wavelengths. So their wavelength is big, but their frequency is small. Okay, so low energy on the radio side, high energy on the gamma ray side, and this should make sense, because if you think about, well, what type of light, if I were to expose myself to it, would be really dangerous, right? Gamma rays make the Hulk and kill cells. That's why we use them to treat cancer. They can also cause cancer. X-rays, right? If you think about it, what does the dentist do when he gives you an X-ray? They leave the room after covering you in a lead vest, right? They're not getting an X-ray a few times a year, totally safe. Getting an X-ray every single day, not safe. UV, this gives us sunburns, right? So you can kind of see, like, the amount of energy carried in the light is high over here on this side, but it's low on this other side. So this equation we can use if we wanted to calculate the exact amount of energy carried by light. You take the frequency, multiply it by Planck's constant, which is just this magic number right here, and that'll kick out some energy number in joules. So this kind of wraps up what I wanted to do as a discussion, but ended up being just a mini video lecture. If you have any questions about this stuff, kick me an email, or I'll ask about it in class on Tuesday. Thanks for watching, and have a good weekend.